Today we want to investigate the failure of classical wave theory in describing photoelectric effect. So we have classical prediction on the left hand side and experimental observation on the right hand side. So in classical prediction, wave is considered having greater amount of energy if the intensity is very high. So with higher intensity, more energy can be given to the surface and able to eject electron from the metal surface. So what they do is they use brighter lights. Okay, let's say red light, they use brighter lights to shine on the metal surface, and they believe that the ejection of photoelectron can happen. They also believe that when intensity is low, energy of radiation is too small. If they use very weak light, okay, it won't cause any ejection of electron. But actually, experimentally, very low intensity light can still eject photoelectron provided they are high frequency radiation. So how do we find out about this point? You see, light, if it is considered wave, we all know that energy can be carried by wave. Okay, carried from this point to the other point. So if the amplitude is high, the intensity is very high. Intensity of the light is very high. So therefore it carries a greater number or a greater amount of energy. So after some time it should be able to strike the electron from the metal surface. Since this is moving sinusoidally, so the electron also is thought to have moved sinusoidally. Okay. However, experimentally, it was proven that in the metal surface, when you compare red light and you compare violet light, since this one has lower frequency and this one higher frequency, it is found that the frequency is the factor to determine the ejection of electron, as long as the frequency is higher than the threshold frequency. Now, each electron is bound to its parent atom. As we zoom in, we know that electron is bound to a parent atom. So we have electronic binding energy. So to overcome this electronic binding energy, there's a minimum requirement, and that requirement is called a work function. It is the minimum energy required to dislodge the electron from the surface. So this work function W equals to HFO. This is called threshold frequency. This is the minimum frequency to overcome for your radiation to come to shine on the surface. The photon, if you use photon based explanation, this photon must have the frequency greater than the threshold frequency of that material, or else it won't eject any electrons. Okay, so this is the only rules governing the ejection of electron. Even if this is a very weak light, weak ultraviolet light, it can still eject electron out of the surface because the frequency of UV light is greater than the frequency of the metal. So emission of photoelectron occurs for all frequency. That's not true. As we have shown earlier just now, if you use red light, it simply would not eject any electron. Okay, this one, no electron is ejected because the frequency of red light is too low, right? So emission of photoelectron occurs only when frequency of radiation exceeds the threshold frequency. That's the experimental observation, and we have to use photon-based explanation. In classical prediction, we have energy of radiation depends only on amplitude and not on frequency. Okay, what that means is, according to classical wave theory, it really depends on the amplitude proportional with energy, proportional with amplitude, proportional with intensity. Okay, exactly by how much amount I do not know, but experimentally we know that the energy of radiation depends on frequency. It can only be true if you use a model called photon. Okay, using quantum theory, showing that energy is quantized in the pockets of energy. Okay, bundle of energy, bundle of discrete energy. So the quantization process relates the energy of the system in the photon by using Planck's constant multiplied by the frequency of the radiation. Okay, and classical prediction, radiation energy is spread over the wavefront. The amount of energy incident on one electron is extremely small. Electron must gather sufficient energy before emission. This shows that if you use wave theory and you have metal surface here, so your energy can only be transferred to the surface at a certain time later, some time later. So it was believed that there should be some time lapse before the electron can be ejected out. But experimentally, there's no such case. If you use the right amount of frequency, you can eject the electron quite almost instantly. Instant ejection. There's no time delay. This can only be true if you use photon based explanation. One photon transfer to one electron, transfer all the energy. Therefore, it can be ejected out quite easily. Like this one, if this photon comes with 17 joule of energy and the work function is 10, electron can be ejected out with 7 joule of kinetic energy. That's the basis of us having the formula HF equals to W plus EK. Okay, so this is 17, this is 10, and this is 7. If you use classical wave theory, there is some kind of time delay expected, as energy, each energy that strikes the surface and strike the electron is very extremely small. Each energy transfer, each continuous energy transfer, because the energy is thought to be continuously hitting on the surface of the metal. So each collision with the surface is actually very small. Since it's very small, it needs to accumulate more and more energy before electron can be ejected out. But experimentally, there's no such thing. We don't see things like that. We see instant ejection. So therefore, there's no appreciable time delay between the absorption of radiation and emission of photoelectrons, even if the intensity is low.